Okay, so now we're going to push a little bit more on this idea of the solutions to a time-independent Schrodinger equation or the eigenvalue problem for an operator, formation operator, that those solutions or those eigenfunctions or eigenvectors, depending on where we're thinking of them in the function space or in the linear algebra space, they form a complete orthonormal basis, meaning that I could then write any function that has the same boundary conditions as a superposition of those, just like I can write any vector as a superposition of the unit vectors of that space. All right, so here's our picture that we want to keep in our mind. We have the x and y of a typical Cartesian coordinate system. We have a unit vector I hat and j hat. And we know that we can write any vector as the x component times this plus the y component times j hat. Okay, so we want to figure out, in some sense, how do we do this for functions? All right, and all we have to do is figure out how to make a scalar product, because that's what we got. How we got this. Vx is nothing other than the scalar product of our vector with I hat. Okay. So the way we're going to do this is we're going to identify the scalar product for functions. If I have two functions, I'll call one u and v. We have to integrate over all space, so I'll just put minus infinity to plus infinity for here. Okay, and then this is defined as the scalar product, which I can write in Dirac notation like this, right? And so that's convenient. So now I have a way of writing down the representation of a vector in any basis I want. Okay, so the basis I'm going to choose, of course, is the basis that we just discovered, right? The set of functions that are the solution to the eigenvalue problem for the Hamiltonian for the particle in the box. How do I do it? I just simply multiply by 1 over here, but I multiply by 1 using the eigenvectors of the Hamiltonian for the particle in the box. So I sum over n, we'll call those phi n v. All right, so this part here is that spectral resolution of the identity. So that's 1, and this is our v. So what do we need to do? We need to be able to figure out what these are. Well, we know how to figure out what these are. These are these integrals. Okay, so what we've done, all we have to do is be able to figure out basically what's the conversion between this and this. All right, so what you're going to do is you're going to have a chance to play around with this a little bit on your own. I'm not going to go through it because I made up a Mathematica notebook that's really kind of self-contained. It explains the ideas, it shows you how you can make a bunch of different functions and how you can approximate them. I mean, it's approximate because no one's going to use an infinite number here. And there's some other, I think, technical mathematics concepts about how perfect an agreement you can have with between a basis and a set of functions. But the basic idea is pretty clear. You can, as long as the function you're trying to approximate represent has the same boundary conditions, and you can use this. Okay. And so that's how we're going to do that. And I'm just going to So I'm going to make the Mathematica file available to you to use. It'll be on Canvas. You'll see it there. All right, so the point is this is not an analogy, this idea that we have functions and vectors. It really is the same thing. So just as I have a length of a vector in a vector space, which I would define as the norm or the scalar product of the vector with itself, all right, then this corresponds to that normalization condition, or we don't have to call it the normalization condition if we don't want to. The function doesn't have to be normalized, but it does have to have some kind of length. When you see integrals without limits, just assume it means all of the space, right? So that is that. If I have two different functions, of course, or two different vectors, I'll just write it like this. Okay, very good. Okay, so in our discussions, we worked out that a superposition of two solutions of the eigenvalue problem for the Hamiltonian, when you make a superposition, you do not get a solution to the time-independent Schrodinger equation. All right, we worked out these two different cases. And then we also considered an more arbitrary one where we put in a phase in here. One of the sections we did it with a phase, the other one we did it with the Mathematica program, which you can all play around with. All right, the point is that this, because when you write down the, when you operate with the Hamiltonian on this, you get 1 over the square root of 2 times the energy of state 1 plus the energy of state 2. Oops, 2. Unless these numbers are the same, which if we have one-dimensional problem, they won't ever be the same. There's no degeneracy there. They can't factor out. So we cannot write this as a single number, as I'll call it n, times the state that we started with. Not possible. That means it's not a solution. It's not an eigenvector. And that shouldn't be surprising. The eigenvectors are the ones that point along these different axes directions. So the whole point of making a superposition is that we're rotating one basis with respect to the other one. All right. All right, so that is, I would say, a pretty important thing to keep in mind about basic quantum mechanics. As we'll see as we go on, the basis of spectroscopy is actually quite straightforward. When light interacts with a molecule, it's going to make superpositions. Those superposition states will have oscillating dipoles. That allows the light to transfer energy to the molecule. An oscillating dipole will always emit light. It will emit light in the same direction that it was excited in, because you have this phased array of dipoles, because it's one field that's making this. The emission will go in the direction of the light that's exciting it. It's out of phase, and so you'll get interference, and you'll see a decrease of transmission when you have absorption. Right? And that decrease of transmission is an interference effect of the emitted field interfering with the laser. And that is really important, because that helps us. If you can think of spectroscopy that way, instead of just gobbling up photons in a beam, then that'll make it much easier to understand what happens when you have multiple fields interacting with the material, when you have short pulses, when you have shaped pulses, when you have sequence of pulses. And all of those are important for modern spectroscopy, whether it's NMR, UV vis, infrared, microwave, everything now is being done. EPR, I should have said. Always interrupt me if I forget to mention that. Okay, so let's get back to some of the key principles of tenets of quantum mechanics. One of them is that all of our operators are associated with Hermitian operators. All of our observables are associated with Hermitian operators. So I'm just going to talk a little bit about the eigenvalues of a Hermitian operator. All right, so the reason why we propose or postulate that the operators that correspond to observables are Hermitian is because of a property of their eigenvalues, as you'll see in a second. So this is the hermiticity, known long before quantum mechanics. It's something that was known, from just straight ahead linear algebra. So let's assume that there's a solved eigenvalue problem for this. So A operating on A gives an eigenvalue A and A. It's convenient to just label eigenvectors by their eigenvalue. That's what this does here. All right, so we assume it's solved. So we have the set of vectors and we have a set of values A. If we multiply on the left by A, the bra version, we're going to get this. This is a number. It can come out. So then we get A times AA. Okay, this just teaches us how to deal with this kind of notation to follow it through. Now, if the eigenvectors are normalized, which would be the correct way to do things, this would equal 1, and you would get A, which is to say that the expectation value of the operator A, provided that the system was in a state of that eigenstate of that operator, will just be the eigenvalue that it corresponds to. Right? Now, if it's in a superposition, it'll be like the average, or the weighted average of all the different eigenvalues. When you go to measure one, you only get one or the other. So then if you imagine repeating this measurement on many times on the same exactly prepared quantum system, then you would get that statistics. All right, so what we're going to do next is we're just going to remind ourselves something about scalar products with complex numbers. And that is, if I swap the order of them, which I can do by remembering my rules of the Dirac notation, then this will be equal to the complex conjugate of the swapped order scalar product. Okay, and then I can do something, which is to say, write A, and I can imagine what happens if I do this scalar, if I do this, the Hermitian conjugate of this, right? Well, I don't just swap them. I also will put in the adjoint of the operator. So of course, A looks like that, okay? But this is equal to A. So this is the same thing as A, which we know is equal to A. But this whole thing is the complex conjugate of this. So that tells us that A is equal to A star. All right? Well, there's only one kind of number that can, for which that can be true. If I write A as a complex number, A is equal to, if A is equal to Z plus IW, usually people do it the other way around. They make Z the complex number of whatever. I started out with A, so this is what I have to do. This is a real number, that's a real number. W, this is just I, plain old I. Right, so A star is equal to Z minus IW. The only way for A to equal A star is if W is 0. That means the imaginary part of A, is equal to 0, the imaginary part. Another way of saying that the imaginary part of a number is 0 is to say the number is real. All right, so what this tells us is that the property of the adjoint, of the operator equaling itself, or self-adjoint is the other term you can use for something that's Hermitian, is that its eigenvalues are real. We didn't have to know anything except just a little bit of structure of linear spaces, scalar products, and then this one definition of what an Hermitian, a property, I guess I should say, of the Hermitian operator. Okay, so the eigenvalues correspond to real numbers. That's good because when you go to your lab, you're going to measure a real number. You can measure things that can get you out parameters that might have complex values in them, but your measurement itself will be a real number. All right, so what are some other review of the Dirac notation to make our manipulations more tidy? Let's just remember, so if I have a vector and I do the adjoint, and if you see a star, just put a dagger, usually, of course, I think the correct, most perfect notation is that you use a star when you know the thing's a number. So here I know it's a number. And you use a dagger when, it could be a vector or an operator or something like that. All right, so this is equal to, this is a ket, this is equal to the bra version of that. If there was a number times this, A times V, that would be equal to V times A star. Notice the swapping of the order. Now, if A is a number, it makes no difference. I can move it wherever I like. All right, so you could also just write that there. If you have an operator, then you swap the order of the operator and the vector, and you put the dagger on the operator. As I said, a lot of these operators that we measure things with are Hermitian, but there's going to be a very important operator that you've already seen, the time evolution operator. It's absolutely not Hermitian. You can see that it has an I in it, and so it's definitely not Hermitian. So the time evolution operator, not surprisingly, we should not think that time evolution is something that would correspond to an observable. As we've already discussed, time in the sort of what physicists would call non-relativistic quantum mechanics, time plays a role completely different from all of the other degrees of freedom. It doesn't have equal footing like it does in relativity. All right, back to scalar products. So if we have UV, this can be written as U adjoint V. We know UV star. We can just follow the rules, right? All right, so it's going to be the star of this whole thing. We're going to swap them. What else did I want to say? I think the other one we pretty much covered. So if you have an operator in there in the expectation, not the expectation, but in a scalar product like this, and we call this, think of this as the vector W, that's equal to UW. All right, and if we do UW star, that's going to equal WU. And that would be equal to V A star U. Right? So it's just basically the same kind of thing as this, it's just depending on how you want to think about it. So we're going to have lots of cases where we want to consider operators operating to the right, operators operating to the left. This becomes very important in the developing the so-called optical response functions. We're going to have a sequence of operators, and they're all going to be operating one way or the other way. And later we'll get to a formulation of quantum mechanics in the so-called Liouville space, which means that we have a density operator, which we then think of again as a vector. So that's kind of crazy already. And then the operators will always be going from left to right, and because then the operators will actually be Liouvillean operator or Liouville space operators, which will be corresponding to commutators in Hilbert space. Okay, so that's basically where we're headed. This was the sort of basic quantum intervention. You have this, you have some Mathematica things to play around with, and then I will pick it up again at our continuation on the time evolution operator.